if the cause is the same, then the effect should be the same. But that intuition is grossly violated in quantum mechanics. Let me give a very simple example which you know. Suppose you have prepared uh, you have prepared a beam of light which is polarized in the vertical direction. So this is the direction of polarization. And you have placed here a polarizing filter which is oriented in some other angle, say 45-degree angle like this. So this is the angle, the direction of polarizing filter. So there was another polarizer which was placed somewhere here, and which was oriented in the polarization was oriented in the upward direction, so that what comes out are all polarized in that direction, and then this one is oriented in a 45-degree direction. What will happen? What will happen is that only a part will pass through, and the rest will be absorbed. And this is something that you know. But the stream that is coming is composed of particles, photons, and photons cannot be further divided. So a photon either goes through or gets absorbed. But the question is that all the photons are in exactly the same state, identical particles, identical photons, all oriented in the up direction, in the vertical direction. So it is actually V. So it is polarized in the vertical direction, and yet some of them pass through and some of them get absorbed, which means there is a conceptual issue here, that even though the particles come in exactly the same state, their fates are different. Now, this is something that many scientists, including Einstein, had difficulty in accepting, and they argued that there must be some ways in which the particles which you are assuming to be identical are not really identical. For example, when we did not know about spin, we assumed the particles to be identical, but later it was revealed that there is something that distinguishes them. The spin can be different. Spin in z direction could be up or down, and so the particles which were earlier assumed to be identical in state, these are not truly identical. And Einstein and many other people, including Planck, Schrödinger, de Broglie, they all argued that there must be some other attribute to the incoming particles which distinguishes them, and due to which some of them pass and some of them get absorbed. The same kind of situation actually also occurs in a situation where you have in the, say, harmonic oscillator, you have a state like, say, A1, psi 1 plus A2, psi 2. So your psi is this. You'll have to put the phase factors here. I'm not putting that. The point is that it is a combination of two eigenstates. Now, if you make the measurement of energy, then the energy actually is undefined because it has two possible energy levels. For this one, there is an energy level E1. For this one, there is an energy level E2. And this does not have any particular energy value. when you make a measurement, you either observe E1 and or you observe E2, and the probability with which you observe E1 will be A1 square, and probability with which you will observe E2 will be A2 square, so on and so forth. So point is that the state is the same. You do something which is identical, but one time you observe E1, another time you observe E2. The fates are the same. The results are different. So this was a point of discomfiture of many people, that here we have some kind of a fundamental role played by uh, probability, and it is different from the way probability is understood in when you study statistics. When you study statistics, the probability of getting a head or tail was 50-50, because sometimes you will get, or if you do the experiment a number of times, sometimes you'll get head, sometimes you'll get tail, and the number of times you get head divided by the total number of throws is the probability of getting head, so on and so forth. So the point is, why couldn't you pinpoint whether it will be head or tail? It was because we did not know the exact condition of the throw. We did not know its momentum, we did not know its angular momentum, we didn't know various things. The speed of wind and things like that, we didn't know. And had we known all that, then the state at the fall of the coin would be perfectly predictable. So in the statistics that you have learned, probability entered because of our lack of knowledge. That is what some scientists argued, that here also probability is entering because of our lack of knowledge. We do not know the entire state of the system. What we are believing to be a superimposition, linear superimposition of two states, is actually not exactly like that. There is something hidden which you do not know, due to which you are unable to predict whether it will be E1 and E2. Had you known that, then it would be perfectly predictable. And similarly, in various cases, you will find this is something that goes through quantum mechanics. So there was a argument, quite a lot of argument, based on this, whether the probability that comes into quantum mechanics is because of our lack of knowledge, or in the language of Einstein, the fact that quantum mechanics is as yet incomplete. So this is one particular problem in quantum mechanics. The argument was that it must have been incomplete. If we know the complete information, for example, the exact state of each particle that is coming, then it would be predictable whether that particle will go through or will be absorbed. This, what I do not know, what they were arguing, that this is something that we do not know, and that's why the quantum mechanics as we know today is yet incomplete. This has come to be known as hidden variables. That means some variables that are there, that's hidden, we do not know. And many people after that tried to develop theories based on hidden variables, but none of that really succeeded. And in the early 1950s, von Neumann, he produced a proof that apparently showed that no hidden variable theory can give the same prediction of experiments as standard quantum mechanics. Which means that since standard quantum mechanics is, as I have taught in this whole course, is experimentally tested, therefore the hidden variables cannot be true. No hidden variable theory can be true. However, later, about a decade later, it was noticed that there was an error in von Neumann's proof, and so that particular issue is yet open. But there was another issue in quantum mechanics. That is, let me go up there. That is the fact that when you make an observation, before that, the state, I mean, a particle does not have a velocity, that particle does not have a position, and things like that. This grossly contradicts our natural intuition formed out of our day-to-day experiences. When I see a ball going and I make a measurement about the momentum of the ball, I can definitely state that what I measure is actually there. That means the ball was really moving at that speed. And that's what I measured. So what I measure is actually reality, a piece of reality. So a position of a particle, the Mars, for example, today it is there somewhere, and I make a measurement of the position, and I can state with confidence that prior to making that measurement, it was there. I mean, its position was there, and I just came to know what it was through the act of measurement. So, in the whole of physics that you have learned so far, the state actually exists. State of that particular system actually exists prior to measurement. But quantum mechanics was insisting, especially what is known as the Copenhagen interpretation of quantum mechanics, that was insisting that no, the state does not exist. It does not have a value prior to measurement. The act of measurement gives it a value. And I have already pointed out, for example, if you have the double slit experiment, you have the double slit experiment. You have a blockade, and you have a slit here. You have another slit here, and light passes through. So light passes through, and well, you know that if you have a screen here, then there will be a pattern on this screen. There will be a pattern on the screen, something like this. If I draw the probability distribution, something like this. But if you make an observation as to which slit a particular particle is passing through, it could be electron, it could be photon, it could be even bigger particles, which slit it is passing through, then it no longer has this interference pattern. It has just a two peaks, because there is a probability of it going through either this one or this one. So it two peaks. So what actually made the difference? The fact that I tried to find out which slit it is passing through, and Copenhagen interpretation will say that the moment you make a measurement as to which slit it is passing through, the state collapses to that particular state, and therefore it no longer is in a linear superimposition of these two possibilities. Either it passes to this or it passes to this. These two possibilities, linear superimposition of that, it gives this interference pattern. While if you do not allow that, then each one will be distributed this way or this way. Ultimately, you have this pattern. So the act of measurement is making this change. Now there was one particular point I have also made in this course. That is, suppose there is a uranium atom somewhere in the universe, and that breaks. That emits a alpha particle, and the alpha particle goes through. But in which direction will it go through? Well, until you have made the observation, you cannot say in which direction it will go through, and therefore it is actually in a linear superposition of all the possible directions of its emission. It might have gone in any possible direction, and only when if you have a detector here, you have detected here, only then the wave function collapses with delta value here in this particular point. And not only that, when the alpha particle is emitted, alpha particle goes out with some momentum, and therefore the remaining nucleus also recoils with a equivalent momentum. And if the direction of motion of the alpha particle is not known, it's a linear superposition of all possible directions, then the recoil is also has all possible directions. And the moment you made the measurement of the alpha particle here, the other one, the remaining nucleus, also collapses in a particular direction, like here. Now, these are sort of very peculiar assertions of quantum mechanics about which Einstein and many others were very uncomfortable. And they insisted that no, all these are happening. We are looking at the nature this way because our understanding of quantum mechanics is as yet incomplete. We need to develop it further. Now, it was basically two types of belief, but this needs to be translated into something that has a experimentally testable prediction. And so, for example, the cat paradox that Schrödinger proposed. You have a box in which there is some radioactive nucleus, and there is a vial which releases poison, and there's a cat inside. So if the radioactive nucleus disintegrates, it will release the poison. The cat will die, but there's no way to know whether it has happened until you open the box. So until you open the box, the cat is in the superimposition state of the cat dead and cat alive state. And when you open it, then only it collapses into either dead or. This is sort of absurd, but it is not experimentable. Well, 1935, Einstein, Podolsky, and Rosen, they proposed a thought experiment which they believed was experimentally testable at some point of time. Maybe not then, but later. So that is what we will come to. But before we come to that point, let us, because that assertion involved entangled states. Therefore, I'll need to recapitulate entanglement a bit so that I don't miss you. Well, I have said that entangled state, between two particles, is that state, the state of this particle, one particle is in, say, a particular space. So state of particle 1 is a member of a space, Hilbert space V, and the state of particle 2 is a member of a Hilbert space W. Then we will say that the particles are entangled. Normally, the state of the particle will be the state of this system of two particles is a member of V direct product W. Now, there are two possibilities. One, that in this direct product space, still the states of the two particles are clearly distinguishable, which means that we will be able to write this as a product of one, just a product of a state in V and a state in W. So if we can write the state of the system as say psi 1 times psi 2, then it is separate. They are not entangled. But if we are unable to write it that way, then we say that it is entangled. Let me illustrate that, exactly what it means. Let me illustrate that using a two-state system. A two-state system like spin, which is up z, down z, a two-state system. But there can be various ways in which to visualize a two-state system. For example, you have a ammonia molecule, NH3, so it has three of the H3, and the N is somewhere here. So it is something like a structure like this. Now the N could be up there or down there. Both possibilities are there. It is also a two-state system. So various possibilities are there by which you can define a two-state system. But for the sake of simplicity in thinking, just assume that we are talking about spin. So there are two particles. The particle one is in the Hilbert space V, or in case of spin, it is just the spin space V, and state of the particle 2. By the way, the entanglement is not only related to spins. Entanglement can be also related to the state as normal psi, a function of x. So that can also have this property, and then it will be calling that as a entangled system. But in order to understand it somewhat simply, we are using spin as an example. So assume suppose well, in the space V, there should be basis vectors. So V has basis vectors. Let's call it E1 and E2. And W has basis vectors. F1 and F2. Well, if this is a spin, you can imagine E1 and E2 to be, in the Z direction, spin up and spin down. These are the bases. In the W space also, it will be spin up or spin down in the Z direction. You can imagine that way, but I'm just using generic symbols like E1, E2, and F1, F2. So a very general, completely general state comprising these two particles, the most general state then can be written as a linear combination of all these basis vectors. So a general state can be written as psi equal to some E1 direct product F1, that is a basis in the direct product space, times one coefficient A11, let it be, plus A12 E1 direct product F2 plus A21 E2 direct product F1 and A22 E2 direct product F2. So what I have done is, these are the bases in the direct product space, and all I have said is that the state is a complete general linear combination of all these possibilities. So this is the most general state. And in specific cases, the A11, A12, A21, A22 will have some values. So we can even write these combinations as a matrix A of A11, A12, A21, and A22. Right? Now, under what condition will it not be entangled? It will not be, the state will not be entangled if I can express uh, uh, if I can express psi as this is in space V and this is in space W, then it is not entangled. So if it is in space V, I can write it as a linear combination of the basis vectors in V. So I can write it as A1 E1 plus A2 E2 and say B1 F1 plus B2 F2. F1, F2 are the two basis vectors in the W space. So this is in V and this is in W. So the point is that the statement is that if there exist A1, A2, V1, V2 such that this is true, then the state is not entangled. Else the state will be entangled. So let us try to work out. I had written this as a sign, and this should be this in order for it not to be entangled. So let me write it. So it is A11 E1 F1 plus A12 E1 F2 plus A21 E1 E2 F1 plus A22 E2 F2. Now I have to distribute it because distributive law is applicable to the direct products. So I can write it this way, that this is equal to A1 E1 times B1 F1. Now E1 is a vector, A1 is a coefficient. So E1 direct product F1. So it is E1 direct product, sorry. It is A1 B1 E1 direct product F1, E1 direct product F1 plus A1 B2 E1 direct product F2, A1 B2 E1 direct product F2 plus A2 B1 A2 B1 E2 direct product F1 plus A2 B2 A2 B2 E2 direct product F2. Now this immediately implies that A11 should be equal to this A1B1, A12 should be equal to A1B2, and so on and so forth. So I can extract these information. A11 should be equal to A1B1, comma, A12 should be equal to A1B2, A1B2, comma, A21 should be equal to A2B1, and A22 should be equal to A2B2. Now, in this matrix, the determinant is A11, A22 minus A12, A21. So let us construct that. The determinant of A is equal to A11, A22 minus A12, A21 is equal to then A11 is A1B1, A1B1, A22 is A2B2, A2B2 minus A1B2, A2B1. So these are numbers, and therefore basically I can see that they are the same, right? So this is equal to 0, they cancel off, equal to 0. So we immediately come to the conclusion that if the determinant of A is 0, if the state is not entangled. And it is easy to understand that this is a rather restrictive condition. For most other conditions, there will be some entanglement. So entanglement is not a very unnatural or uncommon situation. Entanglement is a very common situation. So with this background on entanglement, well, again, let me repeat that entanglement is not a property of the spin only. Entanglement can happen in the spatial state of the system. If the spatial states are linked in the same way, that means in the direct product space of the two individual spaces, if the state of the whole system cannot be written as something in space v and something in the space w, the product of that, then it is entangled. Now, with that background, for example, we have learned that the singlet state is the entangled state in spin. In the triplet state, there is one state which is entangled, the other two are not, and so on and so forth. This is something we learned earlier. So let me delete this and go ahead. Yes.
Excuse me, sir.
Sure.
Sir, when you said that what condition do we need for the particle to not be entangled, for the particles to be not entangled?
Yeah.
You said that when they are expressible in the forms of a vector relating to the V space and the vectors relating to the W space
Yes.
separately,
Yeah. That means essentially.
as the cross product of
Yeah.
these two.
Essentially, just a minute. Essentially, it means that the state of particle 1 is well defined irrespective of the state of the particle 2. Similarly, state of particle 2 is well defined irrespective of the state of particle 1. And in that case, we can write the combined state as the state of particle 1 times state of particle 2. Yeah, now tell me, what is the question?
Sir, then why is it necessary for the determinant of that matrix to be 0 for the particles not to be entangled? We have already expressed the coefficients a11, a12 in the
No,
as
we have read that.
derived from.
Yes, but this is a this state can be entangled, cannot be entangled. It's just a general state, right? This one. This
So
state
when we express this same state,
yes. This is something that is not
so
entangled.
when we equated these two.
No, this is something that is not entangled.
Yes, sir. Yes, sir.
See the line of argument. This is a completely general state, and this is what will happen if they are not entangled, because I have now separated out the state of particle 1 that is in V, state of particle 2 that is in W, and we have sort of factorized the state as something in V, something in W. So this is not entangled. Then we said that what are the conditions on A11, A12, A21, A22 so that the system will not be entangled. So we said that, okay, let this be equal to this, and from there we extract a condition on A11, A12, A21, A22. And then we concluded that the condition is that the determinant of that matrix would be 0. And only then it is factorizable into this form.
Sir, when we equated the general state with the non-entangled state,
Yes.
so we already found a condition on A11, A12, A21, and A22.
Exactly.
Then why at the end are we saying that? Then why at the end are we saying that the determinant needs to be 0? We already found a condition on A11, A12 in terms of A1, B1, A2, B2.
Let me repeat the point. Argument A once again. This is a general state. Okay. This is the general state. Now, there will be a subset of the general state where it will be not entangled, right? And the substate will come in the form of some conditions imposed on A11, A12, A21, A22. Now suppose it is not entangled. So it should be expressible in this form. I'm asking then under that condition, what are the conditions imposed on this? So this is a very completely general state. On that, I'm asking what are the conditions that should be followed by A11, A12, A21, A22 so that the state is not entangled. So what we do, we these are all general values. Huh? These are all general values. This I have not imposed any particular value to this. Now we substitute it here, and the moment I make this equal to sign, it means that I am assuming these A11, A12, A21, A22 are having such values which will allow the states not to be entangled. And then we derive that leads to the conclusion that these should be following the determinant A. So what we have done, we have first written this as a general thing and then said that I want to extract those conditions under which it is not entangled, and therefore we equate this to the non-entangled state, and that leads to the conclusion that this should be the determinant should be 0. Is the point clear now? Okay, how else would
Not completely clear yet.
okay? How else would you imagine that I would, in some possible way, conceivable way, like to extract some kind of a conditions on these four numbers, which will ensure that the state, the combined state of the two particles, is not entangled. How else would you do that? The only way to do that is I write the completely general state, and the moment I put this equal to sign, it imposes the conditions that these are not entangled. So not entangled condition. Huh? I impose the not entangled condition. Therefore, the A11, A12, A21, A22 in this equation are not any general value. They can take only some values, specific values. And then we concluded that those specific values will be such that the determinant will be 0. Do you get the point now? Okay, if you don't, then just let it rest here and let me proceed and think later. Just revisit your class note and think later. I'm sure you will get the point, because this point is not very difficult to grasp.
Yes, sir.
Okay, now let me delete this and let me go to the next point.
Sure, sir.
Now, what Einstein, Podolsky, and Rosen argued is that let there be a condition in which let a pair of entangled particles be generated, say at this point. A pair of entangled particles are generated, and the particles move in opposite directions and maybe a very long distance. It could be from here to Delhi, it could be from here to the Mars, or even another galaxy. So this was a entangled particles. So these are entangled particles. Entangled pair. Now, after some time here, you make a measurement. Say you place a Stern-Gerlach apparatus and measure the state in the z direction. And suppose it is found to be up. Then at the other end, if you measure this, it will be immediately found to be down. They asked, how could the information travel from here to here so that this particle knew that a measurement has been made there, and immediately it took a particular value that is down in the z direction. So how could the information travel from one point to another? That's one problem. The other problem is that they argued that suppose I observe it to be up in the z direction, and this guy is down in the z direction. What is wrong in assuming the simplest possible thing, that when they separated out, they were already up and down? You didn't know. They don't make a measurement, and you find that it is up and this is down. What is big deal in it? So it was actually earlier, right in the beginning, at the point of separation, this guy had a up z spin, and this guy had a down z spin, and so you after some time you measure it. So there is nothing, you don't have to assume that they were in a linear superposition of two possibilities, and then I measure it and then you observe it. So you notice that their line of argument stems from certain assumptions regarding the nature of nature. They were actually assuming what is known as local realism. And the local realism actually asserts two things. First, local means measurements. Realism means measurements correspond to some aspect of reality. So the observables, the meaning of the reality is that observables have values independently of any measurement. Okay, so this is the assertion of what is known as realism. That from that assertion, they were saying that actually this particle had a spin up in the z direction, and this one had a spin down in the z direction, independent of a measurement. What you do actually by measurement is to know it. That's all. Measurement corresponds to some aspect of reality. It was a reality, we just measured it. And local what to say, localism is called is its meaning is that measurement is independent of actions performed at a distance distant location. So location at the same time. The argument is that by special theory of relativity, the information cannot travel faster than the speed of light. So for the information to come from this point to this point, at least it will be delayed by the distance divided by the speed of light, that much of time. So immediately, instantly, the state cannot collapse. So these two are together considered to be assertions of this position, local realism. And many scientists, including Einstein, de Broglie, Planck, Schrödinger, they all subscribe to this view. On this particular point, we have made some progress, and that's what I'll talk about today. But before we do that, I have 10 minutes left. Before we do that, just a recap of the because we will consider the singlet state as an example of a entangled situation. The singlet state is state of two particles. If you recall, that was psi 1 by root 2 to normalize. It was up, down, minus, down, up. Unless we mention something, up, down, all these are in the z direction. And we have the position convention that first arrow relates to the first particle, second arrow relates to the second particle, and so on and so forth. So effectively what we say is this 1 by root 2 is up 1 direct product down 2 minus down sorry 1 direct product up. This is what we have abbreviated like this. So effectively it is like that. And we also know, we have earlier learned, that this looks the same irrespective of the direction from which you look. So this is the same as 1 by root 2. It is up in the n direction, down in the n direction, minus down in the n direction, up in the n direction. So any direction n, it will look the same. So this is something that we have learned earlier. So on that basis, we will proceed. So after Einstein, Podolsky, and Rosen, that was 1935, they proposed this EPR. They wrote this EPR paper. For quite a long time, there was practically nothing done because people sort of they could not answer the questions that EPR had raised, but they thought that this is all philosophy. It doesn't really matter in the day-to-day computation that we do using quantum mechanics. So people simply carried on their activities until the early 1950s, when David Bohm picked it up and said that what if we do it slightly differently? Instead of measuring both in the z direction, if we place the Stern-Gerlach apparatus here in the z direction and here in another direction, not exactly in the z direction, then what will you observe? So it is not difficult to work out what we will observe, because just a bit of recapitulation will be necessary probably. We have already seen this, but let me just quickly recapitulate. The up z was written as 1, 0, and down z was written as 0, 1. This is we have something we have done, so don't ask me to justify. This is in the earlier lectures. And the up n in an angle in an arbitrary direction will be it was cos theta by 2 e to the power I phi sine theta by 2, and our down n was minus e to the power minus I phi sine theta by 2, and here it was cos. And since they were proposing, Bohm was proposing this direction, let it be the y direction, and this is the xz plane, this is the xz plane. When you assume that, your phi becomes 0, so this e to the power something that becomes 0, only the cosine sine terms will be there. And we are assuming that these two have an angle theta. So in that case, he was asking what is the probability that both will be, that means one is in z direction and is in another direction, both will see the particles in up. So it is up in the z direction, up in the n direction. What is the probability of observing that? That is what Bohm asked. In order to, I mean, basically there is an angle between them. But since in the space there is no direction pre-designated as z direction, we can always call one of them as z direction to make our life simpler, the other at a particular angle theta with z direction. So if you take it that way, so one is in z direction, that's why I wrote the up z down z and theta n. So what we so if a particle is in z direction, so if a particle is in state up z, what is the probability of seeing it? That means you are measuring in an angle n, then measure seeing up in the n direction. That is not difficult to work out, because that will be essentially I have up z and I am projecting it on the up n. So it is up n up z. This is what we have to calculate. Okay. And our up n is something we know. So we can write the bra as the bra is cos theta by 2 no, it will be bra up plus sine theta by 2 down. And the up z is this, so we can always very quickly put them together. So it is up n up is equal to cos theta by 2 up plus sine theta by 2 down up, and we know this is 0, so is equal to cos theta by 2. Okay. So the probability of observing up n is a square of that, so cos square. Okay. And similarly, the probability of observing down n is sine square theta by 2. That's easy to calculate. Okay. So a situation on this basis we are trying to calculate. We have a singlet state. Singlet state is I've already written somewhere. Yeah, single state is this, and now we are trying to calculate what will be the probability of observing one here in the z direction up and there in the n direction up. So probability of observing the state is singlet. We are trying to calculate the probability of up in the z direction. Unless you write something, it is assumed to be up, and up in the n direction. This is what we are trying to calculate, right? So effectively, we have to dot it with this bra. And here this singlet. Huh? This is what we have to do. So let us quick. Oh, today the time is up. Sorry. Okay, fine. effectively you understand that what we need to do in order to calculate this is to write up this state in the Brown notation, and then the singlet state is this. So we have to put the bracket and find out what will be the observation. If we do observe that, uh, that means that is experimentally testable prediction. That leads to an experimentally testable prediction. We will continue with that in the next class. If you have any question quickly, you can ask. Otherwise, we'll stop.
Sir, while you did entanglement,
Yeah.
you started with assuming that the state is not entangled and got that the determinant is non-zero. I mean, is zero.
Right.
So on the next sentence, you wrote if determinant is zero, then the state is not entangled.
Mm-hmm.
So that's the converse of what you proved.
Okay. Yeah.
So how did it conclude that?
Yeah. There's an issue there. There's an issue there. You're right. That means if it is not entangled, I know that this is true. That means the determinant should be equal to 0. That means, well, the converse, that means when you have the determinant equal to 0, that means you have a situation where the resulting state equation can be factorized in such a way that it can be written in a form which is only in the V space O times something in the W space. So determinant being 0 means you can write it that way. And there it will lead to the conclusion then it is not entangled. Okay. So if it is not entangled, it is determinant equal to 0. If the determinant is equal 0, it also means that it is not entangled. And if determinant is non-zero, I have not proved that then it must be a entangled state. That is what we have not proved. But what we have proved, that also leads to its converse, that if the state is not entangled, determinant should be 0. And if the determinant is 0, then it is not entangled. This part has been proved. If you look through the derivation, you will see that if the determinant is 0, it immediately leads to the conclusion that the equation that I wrote of a non-entangled state, that it should be true, which means that it should be factorizable. The left-hand side that we wrote, it should be factorizable into something that is only in the V space times only in the W space, which means it is not entangled. But it does not immediately lead to the conclusion. In that sense, you are right, that if the converse means it is not 0, the determinant is not 0, then is it guaranteed that it will be entangled? No, that is not what I proved. Get the point?
Sir, when we are saying if the state is not entangled, then the determinant is 0. The contrapositive is the determinant is not 0 implies the state is entangled.
No, that needs further proof, because I have not proved that some other conditions would not lead to a factorizable condition. I only proved that this condition definitely leads to factorizability. But I have not proved that some other additional condition might also lead to a factorizability. That I have not proved. So this does not immediately lead to the conclusion that the moment you have ensured that determinant is non-zero, it must be entangled. That cannot be guaranteed. That cannot be guaranteed. So in that sense, your point is correct. But what has been done in the class essentially means both ways. If it is determinant is 0, then it is not entangled. If it is not entangled, then determinant should be 0. Both are true. But the contrary is not proved by this. Contrary is when it is non-zero and when the particles are entangled. Do you see the logical issue here? That in order to state that if the determinant is non-zero, it must be entangled, I have to show that no other condition on the A11, A12, A21, A22 can lead to a factorizability. That I have not shown. Okay. Any other question? No. If not, then let us stop here and we'll continue in the next class.